The next thing that you've got on your plate, now that we've gone over the exam solution review, is a submission for the design project. Phase 1 is demand estimation. And the homework you turned in today is where those peaking factors come from. You know that the problem that had the curve and you had to digitize that curve? The 3.25 and 1.8, those peaking factors that you use in demand estimation are derived from that curve. And you'll use that curve a lot more when you're sizing the reservoir in phase 3 of the project. But for phase 1, you're just demand estimation. So we talked in the last class meeting about what that is trying to figure out how many people are in the zone, what's their individual water use, the collective water use, and how does that vary from the average day to the peak hour. So the first thing that I should see when I open up the PDF file is that summary table. And then following the summary table are your supporting calculations. And there should also be, if we just pull up the assignment description here, let me do that. Just to emphasize, so it's the summary table as the first thing, supporting calculations, and a written summary that describes the assumptions you've made, what resources you used, and how things have been calculated. So for example, I should be able to find in that written summary what you assume is the per capita use for each person in the north zone. I should be able to find in the summary how you've calculated your golf course flow rate. Like what kind of watering assumptions have you assumed for that? You know, your assumptions behind the demand at the food processing plant and so on. And tell me about what research did you do to find out the rainfall in your city, or some other method you use to determine how much water has to be irrigated at the golf course. So that written summary is the third thing, in addition to the summary of the calculations and then the calculations themselves. So that's due on Monday, which gives you the weekend to spend some additional time. Any questions related to the project that I could address now before we move on? All right, we're going to watch a video. This is a video that was recorded, it's maybe now 10 years ago, by Dr. Pearson, who is kind of the founder of civil engineering at Marshall. He founded the engineering program at Marshall. He previously was a professor at West Virginia Tech and then got things started here. And he was kind of an expert at the Casio calculator. You already know, I've mentioned before that I use HP calculators, and I'm kind of a babe in the woods when it comes to trying to use the Casio. And so that's why we're going to watch this video. Is you need to be able to solve for an unknown depth in Manning's equation for a trapezoidal channel. So maybe by now you'd be able to write Manning's equation by memory. Let me just put it on the board. The flow rate in a channel is the area to the 5/3 power, the slope to the 1/2 power, divided by the friction factor n times the wetted perimeter to the 2/3 power. All right, so that's Manning's equation. And what makes it tricky is if you have a trapezoidal channel, which is a lot of the time. The reason why trapezoidal channels are so common compared to rectangular channels is it's hard to maintain a vertical slope if you've got natural soil. You can do a vertical slope with concrete or rock, but if you're excavating into clay and sending water down that stream, it's not going to be long before it slumps into the channel and sets itself up into something approximating a trapezoidal shape. So trapezoidal shapes are really common for both engineered structures, but then they kind of just naturally set up when you've got a soil that it only has enough cohesive forces to stay together at a certain angle. So we're going to watch this video because what Dr. Pearson does is he illustrates how you can solve Manning's equation for a trapezoidal channel. So this is what Manning's equation looks like for a trapezoidal channel. So you can see the link to the video in the notes. We're going to watch it. It's maybe only 6 or 7 minutes long, no, 4.5 minutes long. And then later on in class, I'm going to ask you to solve Manning's equation to find the flow depth for a trapezoidal channel. So let me pull this up. We'll watch it. So he mentions that it takes 15, 20 seconds for the calculator to find the solution. I think maybe it's a bit faster now. Like this was one generation removed from the current Casio. Maybe now it'll only take 10 or 15 seconds for it to find the flow depth for you. But this is, let me just put it this way. It's something that's not going away. So you can't outwait having to learn how to do this on your calculator. So you need to be able to solve for the unknown flow depth using a calculator for a trapezoidal channel with Manning's equation. So we'll do an example of it today using the spreadsheet, but you also need to be able to do it with a calculator. Here's Manning's equation if we hadn't yet combined the area and the area inside the hydraulic radius. So when we do combine the area to the 3/3 power and the area to the 2/3 power, then it's area to the 5/3 power. But what this slide is meant to illustrate is that you can rearrange Manning's equation to put all of the known values on one side of the equation. Here they're on the right side. All of the things that would be given, like the roughness that corresponds to the material, the flow rate, the slope. And if we wanted to know the depth, then anything that has y as a variable would be moved over to the left-hand side of the equation. They're both area and here hydraulic radius is a function of the normal depth. And so what we could do with Excel is have the known values on the right, and that would tell us some target for the left-hand side that we're searching for by changing the value of y. So we'll start with a guess value of y, and we'll do a goal seek until we've achieved what depth makes the left-hand side of the equation equal to the right-hand side of the equation. So that's what we'll do in this example. And I've provided a template that's on Excel. It's on Blackboard in Excel. If you've got your computer today, if not, then you can solve it with your equation solver on your calculator. I'd love for you to get the practice doing that. But let's try and find out if we have a channel where the bottom width is 15 meters, and we know that the flow rate is 175 cubic meters per second, and the channel slope, this one's relatively flat, 0.0045, then what would be the flow depth? Okay, so the template that I've provided is here at the bottom of the page, trapezoidal channel geometry example. So if you have your computer, you can open that. I'll give you a moment. You don't have your computer, then you can follow along using Excel. I'm sorry, using your calculator. All right, so the template just has kind of a sketch of what the cross section looks like. So it's got 2-to-1 side slopes where t equals 2 means that for every 1 unit of vertical elevation change, there's 2 units of horizontal distance on the side slope. So if we have a depth of 1 meter, then that means that there would be 2 meters of extra length across the top on the right side and 2 meters of extra length across the top on the left side. So if the depth was 1 meter, then capital B, the top width of the channel, would be 15 plus 2 plus 2, so it would be 19 meters is the top width. All right, so let's put in the details we know and set this up to try and find out what would be the flow depth. What's the required flow depth to accommodate 175 cubic meters per second? Okay, obviously Q here is 175. Okay, lowercase b means the bottom width of the channel. So we can see that it's 15 meters of width on the bottom of the channel. The n value is the roughness, which is determined by what the channel is paved with. Here, the 0.013, that's a typical n value for concrete. 0.013. Okay, the slope of this channel was 0.0045. That was given here at the beginning. And then T, the side slope factor T is 2. All right, so we want to calculate this intermediate quantity W because it's going to be used for the wetted perimeter. So you can see that the table that we've got, I think it's table 10.1, says that W is 1 plus T squared to the 1/2 power. Okay, so W is 1 plus T squared to the power of 0.5. You don't have your spreadsheet, you can just do these calculations by hand for now. Okay. Now, we don't know what the flow depth is, but we can start with a guess. And the same thing happened when Dr. Pearson was setting it up in the Casio. Like, it's prompting you, once you type in the formula, the next thing it prompts you for is it wants to know what number to assign to each of the variables that go into the formula. And even for the unknown that you're trying to solve for, you still have to give it an initial guess. And hopefully it should be a guess that's relatively close to what's accurate. If, he was saying if you give it a negative value or a nonsensical value, it may converge on a different root of the equation. But let's just say that the flow depth is 1 meter as our starting guess. All right, so if the flow depth is 1 meter, then we need to find out what would the area be. So here we can use this formula to tell us what would be the area if the depth is 1 meter. So area is equals parentheses b plus ty times y. So here's b plus t times y, and then close the parentheses there and multiply it by y again. Okay, so if the depth is 1, then the area would be 17 square meters. And now the wetted perimeter also is going to be just based on this guess of our depth. So the formula for wetted perimeter you can see is b plus 2y times w. So equals b plus 2 times y times w. Okay, and then R sub h, hydraulic radius. It's the area divided by the wetted perimeter is the hydraulic radius. So equals area divided by wetted perimeter. LHS means the left-hand side of this equation. So the left-hand side is area times the hydraulic radius to the 2/3 power. Okay, so equals area times the hydraulic radius to the power of 2/3. So I'll just type in 0.666667. So this is the left-hand side of the equation if the y value is 1. The right-hand side of the equation isn't going to vary based on y. It's just this n times q divided by the slope to the 1/2 power. So the right-hand side of the equation is n times q divided by the slope to the 1/2 power. Okay, they're not equal. So that tells me that because the two aren't equal, that I don't have the right guess for y. And so I could just manually type in a different y and see if it gets me closer to the left-hand side and the right-hand side being equal. Or I can automate the process with goal seek. And so this difference cell is just find the difference between these two. And it doesn't matter if you have right-hand side minus left-hand side or vice versa, because we want the difference to be 0. All right, so here in the Data tab, What If Analysis, Goal Seek, our goal is that we want the difference to be 0 by changing the depth. So we have this initial guess, and we're giving Excel permission to keep changing the value that's in cell B12 until the difference between the left-hand side and the right-hand side are 0. So when I click OK, in just a blink of an eye, it'll go through, try a bunch of different depths, and then this is suggesting that the depth should be 1.57 meters to give us the flow rate that we need. And we could check that. Of course, the way to check it is just put it into Manning's equation. Calculate what is the area for this depth. So the area for that depth, calculate slope to the 1/2, divide by n, divide by wetted perimeter to the 2/3 power. And what you'd get, to double check, is you'd find out that this channel has a capacity of 175 cubic meters per second. All right, so did anybody manage to solve it on the calculator? And did it converge on the right solution? You got it. Good. And how long did it take once you said compute?
It took like 10 seconds.
10 seconds? All right. Yeah, they don't put like the latest Intel chips in those Casios. But I'm glad it got it. That's good. So if anybody needs help figuring out the Casio, there's the video, and then there's these two on the front row who know how to run the Casio. Don't come to me, because I don't know how to run the Casio. I could maybe figure it out with you. You can come to me if you need help. We'll figure it out together. Any questions about this example before we move on? All right. So table 10.1 doesn't just have the trapezoidal geometry. It's got the geometric parameters for a wide range of different channel shapes. It's got this triangular channel, if you had it coming to a point at the bottom rather than some certain width at the bottom. The circular pipe geometry is pretty important in sewers and storm sewers, where most of the time water is flowing through a circular conduit, but it's not full to the top of the pipe. So you can see that the method to find out what's the area and wetted perimeter and so on depends on measuring the angle. So here theta, you can determine theta by the ratio of the depth y to the pipe diameter d. And then once you know the angle, you can, and it'll be in radians, by the way. Once you know the angle, then you can put it into these formulas. So just be aware that those geometric parameters are available for you in Chapter 10. All right, let's practice with one more open channel here. I'm going to, rather than talking you through this one, I'm going to pause and allow you to use either Casio calculator or just manual iteration where you're trying and updating different y values, or the same approach that we did just now. But we have a 3.5 meter bottom width. The channel slope is 0.1%, so you'd need to put that into Manning's equation as 0.001. The n value is 0.014 for smooth asphalt. And we want to know what's the flow depth if we're trying to accommodate 29 cubic meters per second. So if you did follow along with this last example, you could create a copy and then just adapt. But But let me pause for a second and see if you can find out what will be our flow depth, why not, for steady, uniform flow. So this is where there's no obstructions upstream or downstream, nothing disturbing the flow. It's just set up at whatever depth is going to be there based on the relationship between the slope of the channel and the energy that's lost due to resistance. Looks like it should be 1.66 meters. I think those of you who already had the equation in the calculator, it stayed there and just had to update some of the parameters. I had the formulas in the workbook, so all I needed to do was update the bottom width, the roughness coefficient, the slope, the side slope factor, and so on, and then run goal seek again. So we've mastered the trapezoidal channel geometry for Manning's equation. At least for now. Things get tricky when you have non-uniform flow, like when water is approaching a waterfall and it starts drawing it down. Then it's a little more complex. We can't just apply Manning's equation to find out the flow depth. Any questions about this example? Well, if not, I think we're done. We'll leave it there for today. Remember that the next thing that you need to submit for this class is phase 1 of the project.